So in this video we want to introduce second partial derivatives. And the idea is just like when we're working with a function of a single variable, we can take the first derivative of a function and then find its second derivative by taking the derivative of the first. We can do the same type of thing when we're working with functions of two variables. And the idea is because we have a function of two variables, when we take the first derivative, we have two choices. We choose to take the derivative either with respect to the x variable or the y. And then in step 2, we take the derivative of that previous result. We have two choices again. We can either take the second derivative with respect to the x or the y variable. So we get 2 times 2 is 4 ways to make second derivatives from functions of two variables. So the typical notation is going to be like this. We do f sub xx. This means take the derivative with respect to x, then with respect to x again. We could also say take the partial x of partial f partial x. Or we can use the notation seen here where you superscript a 2 in between the partial symbol and the function in the numerator, but put the 2 with the x in the denominator. So these are all 3 ways of saying take the second partial derivative with respect to x after taking the first partial derivative with respect to x. So the second part, f sub xx, the second partial derivative. We can do it with respect to y both times. So do it with respect to y, then do it with respect to y again, or take the partial derivative of f with respect to y, then take the partial y of that result. We also can do mixed second partial derivatives, where we first take the derivative with respect to x. Notice that the thing that you do first is up against the function symbol. So first do it with respect to x. First do it with respect to x. Take that derivative with respect to x. Then take the partial with respect to y of the partial of f with respect to x. So f sub x y. And when we use the subscript notation, the thing on the left is done first, followed by the thing on the right. And this is more of a composition notation where we do this thing first, the thing on the right, and then the thing on the left. So you want to note this one has a right to left orientation, and this notation has a left to right notation. Do x first, then do y. So this would say take the partial derivative of f with respect to y, and then take the derivative of that result with respect to x. Take the partial derivative of f with respect to y, then take the partial derivative with respect to x of that result. So notice notice the orientation. It's y first, then x. It's y first, then x. So it's a right to left orientation versus a left to right orientation, depending on the notation that you're using. So best way to do these is just to do a concrete example. So this is find all second order partial derivatives for our function f equals x squared y minus y cubed plus the natural log of x. So I'll take my function f of xy equals x squared y minus y cubed plus the natural log of x, and first take the first partial derivatives. So take the partial derivative with respect to x. So the partial derivative with respect to x, we hold y as a constant coefficient on the x squared term. The 2 is going to come down, so we're going to get twice y times x. We're reducing the exponent by 1, so we get x to the first. The y cubed term, we're going to treat the y cubed as a constant, so we get the derivative being 0 with respect to x, plus the natural log of x. The derivative of the natural log of x with respect to x is just going to be 1 over x, or we can write that as x to the negative first power. We can also do the first partial derivative with respect to y of our function, and if we're doing it with respect to y, then we're holding the x terms as constant. So we're going to look at x squared as a constant coefficient on y. So the derivative of a constant times y is just the constant. So the derivative of x squared y with respect to y will be x squared minus The derivative of y cubed with respect to y is 3y squared. And the derivative of the natural log of x with respect to y will be 0 because we'll treat the natural log of x as a constant. Once I do that, I can calculate the second partial derivative. So I can calculate f of xx, f sub xx. So I've already taken the derivative with respect to x. This says do it one more time. So I go to my partial derivative with respect to x, and then I take its derivative with respect to x again. So the derivative of 2yx, we're treating this as a constant, so we get 2y. And then the derivative of x to the negative 1 will be minus x to the negative 2. I can also calculate the partial derivative f sub xy, because this says take the derivative first with respect to x, which I did right here, then take the derivative of that result, but do it with respect to y. So doing this mixed partial, we'll take the derivative of this with respect to y. So the derivative of 2yx with respect to y, we hold the 2 and the x as constants, so we'll look at this as look at the y as having a coefficient of 2x. So we'll get 2x is the derivative of 2xy, and the derivative of x to the negative first power when we're taking the derivative with respect to variable y is just 0. So our mixed partial f sub xy is going to equal 2x. Then I can step over here and calculate f sub yy. So take the derivative with respect to y, which we've already done right here, then take the derivative with respect to y again, and the derivative of this with respect to y, the x squared will be constant, so we'll get 0 minus 3 times, the 2 is going to come down, so we're going to get minus 6y as our mixed partial, where we take the derivative with respect to y both times. I can also from this calculate f sub yx, because do y first, we already did it, then take the derivative of that result with respect to x. So the derivative of f sub y with respect to x is going to equal right here 2x. We treat minus 3y squared as a constant, so its derivative 0. So there's all four mixed partials, and then what we want to notice right here is that the mixed partials f sub xy, f sub yx are actually equal to each other, and this is going to always be the case. It's going to be the case that f sub xy will always be equal to f sub yx, which we'll show a proof of in the subsequent video.